It slips in from the deep between the stars, small against the sun, yet heavy with questions. We call it Three-Eye Atlas, the third interstellar visitor on record, and from the first nights its behavior nudges at our instincts. It comes fast, it brightens and fades on a schedule set by the lamp we orbit, and then it aims for a sweep near the sun at the very time Earth-based viewing becomes hardest. That timing alone is enough to make seasoned observers sit forward. We remember how Oumuamua defied simple models, and how Borisov behaved like a textbook comet. A third case is not just another guest. It is a mirror held up to our pattern-seeking minds. There is more. A machine trained on countless sky tracks weighs the geometry and tags this path as unusual within its learned catalogue. Unusual is not a verdict, it is an invitation, and the invitation is sharp. Are we looking at a beautiful coincidence written by gravity and perspective, or something that borrows the look of nature to travel with purpose? The difference matters less for drama than for how we plan the next months. Before we choose a story, we need a clean map. What exactly qualifies as an interstellar object? Why do viewing angles near the sun erase the details we crave? Which dates and distances truly matter for instruments in the United States and beyond? If we lay out the timeline without romance, what does it show us next? The cleanest way to keep our balance in a story like this is to draw a map before we draw conclusions. A map is not a promise of revelation. It is a way to decide where to look, when to look, and how to read what we find without losing our footing when the plot gets loud. So we start simple. An interstellar object is a body that does not belong to the sun. It arrives from elsewhere on a path that does not close into a loop. Its speed is high, its time in our bright neighborhood is short, and our window to study it is measured not in years but in weeks and months. That is the headline. The fine print is geometry. Geometry decides how hard the job will be. Picture 3 points in space: the sun, Earth, and the visitor. If the line from Earth to the object passes close to the sun's face, the glare washes out contrast. Ground-based telescopes lose the delicate detail they need, and many space telescopes have strict safety rules that keep them from pointing too near the sun. The cruel twist is that the object is often most active near the sun when heat and light are strongest, which is also when our view is worst. The calendar calls that stretch a blackout. It is not mystical. It is a known cost of living next to a star. Before the blackout, there is a chase. Survey telescopes pick up motion and post coordinates. Follow-up teams swing their mirrors and tighten the orbit, turning a smeared curve into a track with uncertainties that shrink as nights go by. Photometry teams measure how bright the object is at different angles to the sun and Earth. Spectroscopy teams spread their light into colors to look for water ice, carbon compounds, and minerals that tell us something about the surface and the coma. Radio and infrared groups listen where dust and gas tell different stories. Each group speaks its own language, and the event map translates those languages into milestones the public can follow. The first milestone is confirmation. Does the path truly show that this body is not bound to the sun? The check is whether the orbit is hyperbolic, which in plain words means the track will not close. Once confirmed, the second milestone is refining the time and distance of the pass near the sun. That date carries practical meaning. Observers in the United States and elsewhere can look ahead on their schedules and mark the days when the object will be too close to the solar glare for safe or useful viewing. That is when the ground quiets and we wait for the object to come out again on the other side. Fainter because it is farther, but viewable because the glare has eased. Between now and blackout, we count opportunities by angles. Phase angle is the angle between the sun, the object, and the observer. It sounds technical because it is, yet the idea is easy. A baseball looks different under a lamp when you stand in front of the lamp or off to the side. The surface looks smoother in one position, rougher in another. The coma looks thicker or thinner. The tail glows or fades. When an event map says that a certain week is a good phase for a certain measurement, It is telling photographers when the light will flatter the subject in a way that reveals something useful rather than merely pretty. There is another line on the map that matters to anyone who wants to understand why teams disagree at first and converge later. Early astrometry, those careful measurements of position against background stars, is noisy. A small error today becomes a big difference in weeks. That is why event maps talk about uncertainty envelopes rather than single lines. As more points are gathered, the envelope tightens. The point of repeating this in public is to turn revisions into normal updates rather than shocks. When a date shifts or a distance changes, that is not the story breaking. That is the story getting sharper. The blackout period deserves its own paragraph because it invites drama. The timing of 3II Atlas near the Sun will make Earth-based viewing difficult at exactly the moment curiosity peaks. Read that sentence slowly. Difficult does not mean impossible everywhere. A probe near the Sun views from a different angle than a telescope on the ground. A spacecraft at a different point around the Sun sees a different phase of the event. The event map should list which non-Earth-based assets can try what and when, and which of those attempts are long shots. It should also remind the audience that safety limits exist for a reason. Pointing an instrument too near the Sun to chase a headline is not clever. It is foolish. Our job is to plan attempts that respect the hardware and still give us a chance to catch the pieces of the show that matter. After a blackout comes recovery. The object emerges from the glare into darker skies. It is farther from the Sun, so activity may be lower, but the view is cleaner. That is when you refine rotation, texture, and any lingering questions about composition. If any planetary flybys occurred within ranges that put the object inside instrument reach for probes near those worlds, you check whether those platforms captured anything usable. The key is not to promise a grand reveal on a date circled in red. The key is to promise that you will compare pre-blackout and post-blackout behavior and say what changed, and that you will present null results with the same pride as the hits. Now we move from the sky to the network that reads it. The United States lives under a sky served by survey telescopes in Arizona, California, and Hawaii, by academic observatories across the country, and by space-based platforms owned by national agencies and international partners. Add to that a citizen astronomy community that can fill in gaps when the big mirrors are clouded out or overbooked. An event map that treats this network as a single instrument will assign roles. Surveys catch motion and offer alerts. Big mirrors take deeper exposures for size and spin. Infrared platforms sniff for heat and ice. Radio arrays track charged species in the tail. Amateurs gather high cadence light curves that capture flicker. No big telescope can afford to chase night after night. A shared calendar aligns these pieces. A shared glossary keeps words from drifting. A shared image repository holds raw frames and calibrated products, with credit assigned in the open, so small contributors see their work on the same stage as the giants. Because the idea of machine intelligence has become part of the public imagination, our map has to place it properly. A model trained on many orbits can flag a path as unusual. That word is useful if it directs attention. It becomes misleading if it is treated as a verdict. The model knows what it was taught. If you teach it a catalogue dominated by ordinary comets bound to the Sun, an interstellar track will light up for reasons that have nothing to do with intent. If you teach it a richer catalogue that includes simulated visitors with many starting conditions, its sense of unusualness will change. The event map should state how the model was trained and what question it was asked. Then it should park the label in the same corner as any other early clue. Interesting, not decisive. The map also sets expectations about size. When a body is unresolved in images, brightness stands in for diameter only after you guess how reflective the surface is and how the shape presents itself to the Sun. Change the guess, change the number. A fair event map expresses size as a range, not a single figure, and reminds the audience that ranges shrink with better phase coverage and better calibration. In the first weeks, the range is wide. As the object swings around the sun and offers more views, the range narrows. If that narrowing pushes against a favorite narrative, the narrative yields. The map does not. There is a quiet rhythm that any American viewer can learn to follow in a case like this. When a new detection appears, expect 3 to 5 days of quick updates as teams pile on measurements and the orbit firms up. Expect a slower period while proposals are considered and schedules are reshuffled. Expect a burst of images and spectra as the first coordinated campaign runs. Expect a lull during blackout, where space platforms carry more of the load than ground-based telescopes. Expect a second wave of updates when the object emerges again and a comparison with the first wave becomes possible. Expect corrections. The corrections are not failures. They are the cost of learning in public. Planetary passes, if any, add a special beat to the song. A pass tens of millions of miles from Mars, or a similar distance from Jupiter, sounds intimate in public speech and standard in orbital mechanics. What matters is not whether the distance sounds small to a human ear, but whether the distance puts the object within range of instruments that can do more than take a blurry picture. If a probe has a camera that can resolve the coma from that distance, we mark the attempt. If a magnetometer can feel the drape of the solar field around the object from that vantage, we mark the attempt. If neither is true, we temper expectations and let the pass be a detail rather than a drumbeat. There is one more layer on the map that protects us and everyone from confusion. Space weather is an actor with a loud voice. The sun launches shocks and streams that reach different places at different times. When those disturbances hit the coma and tail, structures shift, sometimes dramatically. If the public sees a tail disconnect near a headline date, they will pair the two in their minds. A clean event map places the solar disturbance on the same timeline, noting when it left the sun, when it hit monitors near the sun, when it crossed Earth's orbit, and when it would sweep over the visitor's position. That way, a kink in the tail becomes a piece of physics to be tested, not a blank canvas for mood. This discipline of mapping is not busy work. It is the difference between a season of rumor and a season of learning. It keeps journalists from promising a revelation on a Thursday, when Thursday is simply a day when geometry is unkind. It helps teachers turn a news cycle into a classroom exercise. It gives creators a stable scaffold to tell a big story without leaning on mystery for mystery's sake. Most of all, it gives scientists a contract with the public. We will say what we expect to see and when. We will show our notes when we are wrong. We will not dress guesses as facts. We will not bury null results. The last step in this part of the journey is to set up the comparison that everyone is waiting for. 2 interstellar visitors have already taught us humility in opposite ways. One looked strange enough to provoke sharp arguments. One behaved exactly the way our textbooks said a comet should. A third case enters under that double shadow. The natural impulse is to reach for a ruler made from the first 2 and measure the third against it. That is fine if the ruler is honest about its own rough edges. The wiser move is to let the first 2 teach us how to think rather than what to think. What exactly did they show about shape, spin, outgassing, and the way small forces nudge a path over weeks? What did they show about our tendency to fill gaps in data with favorite ideas? If we answer those questions cleanly, we can walk into the comparison with clearer eyes. So the map is on the table, the blackout is marked, the post-blackout window is circled, the likely planetary distances are listed with what they do and do not allow. The expectations for size and spin are framed as ranges. The role of machine labels is acknowledged and kept in its lane. The calendar carries room for surprise and room for patience. With that in hand, we are ready to step into the precedents that set the tone for every conversation that follows. What did Oumuamua truly teach us about how a small, fast, faint object can mislead, and how Borisov reminds us that normal is still a category in interstellar space? The first interstellar visitor did not arrive wearing a banner. It arrived as a faint streak on stacked images from a Hawaiian survey, a moving point that did not fit comfortably inside the family of paths tied to the sun. In a matter of days, the community realized it was on a hyperbolic course, a track that would not loop back. The next puzzle was brightness. Its light rose and fell steeply as it spun, implying a shape far from spherical. A compact, gently tumbling rock would have produced a modest, regular rhythm. This object's rhythm swung hard, as if a long shard or a flattened chip were flashing different faces at the lamp. To add to the discomfort, its motion deviated slightly from the line gravity alone would have drawn. The deviation was small and persistent, the kind of nudge we often attribute to gases pushing off a warming surface. Yet telescopes failed to see the usual coma and tail that make such pushes visible in classical comets. That combination launched a thicket of explanations. One family of ideas kept everything natural. Even without a bright, dusty coma, a trickle of gas can escape and impart a push that orbit fitters must include. A crust can trap jets and rechannel them in ways that hide obvious signatures. Exotic ices can sublimate without leaving the kind of dust that photographs well, especially if the grains are large or the mixture is unusual. Another family asked whether sunlight itself could be the pusher. Light pressure can nudge thin, low-mass objects the way wind nudges a sail. If the area-to-mass ratio is high enough, a gentle, constant pressure will show up as a measurable drift over weeks. In that lens, the strange light curve hinted at a sheet or a thin shard rather than a compact stone. A few voices took the next step and asked whether a manufactured sail could be the simplest explanation. The debate carried as much mood as math, because the data were sparse and the metaphors were vivid. Time changed the argument less than patience did. As models matured, teams tested how different shapes, spins, and surface properties could fit the light curve, while keeping the mass and area within plausible bounds. Others explored whether low-level outgassing could account for the orbital nudge without leaving dust bright enough to see in standard bands. Neither camp claimed victory. Both camps learned something they did not know they needed to know. They learned how far a light curve taken at poor phase angles can mislead. They learned how much a small, fast, faint target punishes assumptions baked into software pipelines. They learned how quickly a careful description can be translated into a loaded headline when the world wants a story. What matters most about Oumuamua is not which explanation you favor today. It is the habit it taught. When you have a handful of nights to observe, the shape you infer will be a range, not a portrait. When you see a small, non-gravitational term in the orbital solution, you treat it as a symptom to be modeled, not a clue that must point to a single cause. When you cannot find dust, you do not jump to absence. You say that your instruments did not see what they would normally see, and you work through the reasons from the ground up. This is not caution for caution's sake. It is the only way to keep inference from running ahead of exposure time. 2 years later, the second visitor changed the mood simply by behaving. Borisov looked like the comets we grew up with, even as it came from beyond our neighborhood. Its coma was visible. Its tail was photographed cleanly. Its spectra showed familiar species. The orbit was as interstellar as the first case, but the physical behavior calmed nerves. The comparison was powerful precisely because it was so ordinary. If one traveler from another system can look textbook, then the class of interstellar visitors is not automatically a class of outliers. Somewhere in the distribution, there are bodies that carry the usual mix of ice and dust, and that announce themselves in the familiar ways as they warm. That ordinariness taught a second habit. It reminded everyone that novelty at discovery does not guarantee novelty in nature. Our surveys are biased. We notice what we can see and what our geometry allows us to see. We are more likely to follow an object that presents a striking light curve or that crosses a patch of sky at a convenient hour. We undercount faint, slow, or ill-placed travelers, even if they exist in large numbers. Borisov's lesson was that sampling and selection can paint a narrative that later data will sand down. It invited humility without demanding boredom. Taken together, the pair became our first rulers. One ruler says a small, fast, faint object can confuse us in ways that reward restraint. It also says that forces other than gravity matter at the margins, and that our models must carry room for them. The second ruler says that a visitor from elsewhere can follow the same playbook as local comets. It also says that when the usual signatures appear, the field advances fastest by doing the unglamorous work of measurement rather than trading metaphors. Neither ruler is precise. Each has dents and ink smudges where debates rubbed hard. But rulers do not need to be perfect to be useful. They need to be present when the next measurement comes in, and strong enough to keep the conversation from drifting into pure mood. The social echoes of those two cases linger. Oumuamua became a character in a cultural story about technology and the unknown. It showed how quickly an evocative analogy can outgrow its parent paper. It also showed that the public is willing to hold two ideas at once when those ideas are offered honestly. People can entertain a technological possibility without demanding a confession from the sky, and can learn why a natural account remains plausible when you work through the physics. Borisov showed that the ordinary can be beautiful. It drew new eyes to spectra and light curves, and took some oxygen away from the idea that every interstellar object must be a provocation. That recalibration matters because it gives the third case a fairer ring to play in. Both precedents also forced a quiet upgrade in craft. Survey teams tuned their pipelines to handle fast movers without smearing and to propagate uncertainties in a way that does not overpromise. Observers built checklists that prioritize measurements that can break degeneracies early rather than chasing pretty pictures that teach little. Orbit fitters learned to incorporate physically grounded thrust terms from the start, instead of treating non-gravitational effects as featureless knobs. Communicators got better at printing ranges rather than single values, and at repeating the idea that an uncertainty band is not a dodge, but a measurement in its own right. None of this is glamorous. All of it raises the floor under the next debate. There is another inheritance the pair passed on to the age of machine inference. Train a model on thousands of bound comets and thousands of asteroids, and a visitor with a hyperbolic path will look strange for reasons that have nothing to do with intent. Enrich the training set with simulated interstellar fly-throughs across many entrance angles and speeds, and the sense of strangeness will shift. Oumuamua taught us to treat a flag from an algorithm as an index card, not a verdict. Borisov taught us that a low, unusual score does not mean uninteresting science. In practice, the healthiest workflow puts the algorithm at the front door as a sorter, and the humans at the table as judges who check both the training diet and the question that was asked. If the question asked the machine to spot rare combinations of geometry and brightness behavior, a low rarity score is not a comment on whether a hidden mechanism exists. It is a comment on data shape. That distinction keeps a label from turning into a cudgel. The first two visitors also exposed our cravings. We want a clean arc that moves from detection to identity to meaning in days. Nature is not built for that pace. Oumuamua left a permanent bruise on our taste for certainty. Borisov applied a cool cloth to the bruise without erasing it. Between them, they trained us to let some stories stay open for seasons. That training will be tested by 3i Atlas, which arrives with a built-in spike of attention because it is the third, and because early geometry hints at a visibility dip near the time we want to look hardest. The danger is not that we will miss a revelation. The danger is that we will frame the story so tightly that only a revelation will satisfy. So what specifically do these rulers ask of us as we look at the third case? They ask us to keep shape and spin as hypotheses, not identities, until phase coverage improves. They ask us to treat small orbital nudges as prompts to test families of models, not as tickets to a single narrative. They ask us to remember that a bright or dim turn in the light curve can owe more to viewing angle than to interchange. They ask us to check our training sets and our priors when an algorithm tells us a path is odd. They ask us to write down predictions we are willing to be wrong about, and to publish misses with the same rhythm as hits. Most of all, they ask us to keep room for both possibilities that make honest sense. A route that looks efficient can be a byproduct of geometry and selection. A route that looks efficient can be a sign that someone else has learned the same physics we use to tour the planets. These are not equal in probability by default. They are equal in the dignity with which they should be tested. There is one last, human-sized note. Both cases whisper when the conversation grows loud. Let language work for you, not against you. Words like sail and shard carry pictures with them. Pictures travel faster than caveats. If you must use them, put numbers in their company. Say what area to mass ratio would let light push a body the way the fit suggests. Say what spin rate and shape would be needed to match a measured light curve. Say what alternative mixes of ice and dust could hide expected emissions. Swap either the loaded word or the hollow word for the sentence that names the physics. The public will follow you there. It is how they learn to hold uncertainty without being asked to love vagueness. The stage is now set for the question that makes nerves sing. When a path appears to skim more than one planetary neighborhood, when a visibility dip coincides with the moment we most want a clear view, when a machine calls the pattern unusual within its catalogue, what is the fairest way to separate a clever route from an accident of perspective? The answer begins not with a verdict, but with a lens. We take the geometry apart, we put the fits on the table, we map how small early errors balloon, and we ask what counts as an efficient path in a world where gravity and sunlight are the only tools. That is where we turn next, not to declare intention or chance, but to understand what an unusual route really means and how to test the stories it tempts us to tell. Stand with a star map in your hands long enough, and the lines begin to look like intention. Our eyes love plans. But a path through a gravity field is not a highway with signs. It is a sentence written by initial conditions, by light and heat, by a few small tugs that add up over weeks. With 3 IATLAS, the sentence reads clean at first glance and then grows thorny. Early frames turn into a predicted sweep that seems to thread more than one planetary neighborhood, and the timing of its turn near the sun overlaps the weeks when Earth-based eyes are least effective. That combination feels like a nudge from a mind. It also fits the kind of coincidences a large, restless system produces when you only notice the cases that shine. The first step is to slow the movie down. A discovery produces a handful of sky positions with timestamps. Those dots are fitted to a curve against a background of stars, whose positions we know to exquisite precision. The fit begins with gravity alone. Then the modelers decide how much room to leave for small forces that are not gravity, the kind that arise when sunlight warms one side of a lumpy body and gas drifts away. A tiny offset today becomes a meaningful change weeks from now. If you nudge a canoe at the start of a river, you do not have to shove it again to make a bend happen downstream. That sensitivity is not a flaw in the model. It is the nature of flows. From that sensitivity sprouts the illusion of aim. When the curve later grazes more than one neighborhood, our language borrows from mission design. We talk about tours and waypoints. We picture a planner stacking gravity assists the way engineers do when they sling a probe from planet to planet. The resemblance is beguiling because our probes and a natural visitor both live under the same physics. The truth behind the metaphor is subtler. The inner system is filled with moving targets. Throw enough stones through the dance, and a few will trace lines that rhyme with human itineraries. Those are the lines you notice, share, and remember. The rest are forgotten curves that never make a headline. Selection plays another trick that turns chance into choreography. Our surveys are far more likely to spotlight paths that pass closer, even if close still means tens of millions of miles. A path that briefly aligns with our night sky and produces a neat sequence of angles is more likely to be measured well. That edited catalogue is the one we train our instincts on and the one our algorithms learn from. When a rare visitor then lands in the sweet spot for both eye and code, the word unusual blooms. Useful, yes. Final, number. The label tells you what your diet has been, not what the universe intended. Geometry near the sun tightens the knot. As 3i, Atlas sweeps inward, The line from Earth to the object runs close to the solar face. Glare floods sensors. Safety rules limit pointing. Even when you can aim close, contrast drops, and the noise rises. The weeks when the object is most energetic are often the weeks when our largest mirrors must look away or accept degraded data. The blackout that follows in the public's mind has a simple cause in physics and policy. It becomes mysterious only when told as a disappearing act. A cleaner tells respects both truths at once. The timing is frustrating, and it is normal. Direction adds spice. Most of the solar system moves with a family sense around the sun. A visitor from elsewhere often cuts across that flow at a steep angle or even against it. To road-trained eyes, that looks like a driver going the wrong way for a reason. A better picture is a leaf skimming across a stream while fish swim along it. The leaf did not choose the fish's lane. It keeps the path it carried from elsewhere until the currents bend it. That is not defiance. It is an inheritance. Talking about design without turning the sky into a stage requires one more tool, and that tool is energy. At interstellar speeds, even small course changes demand serious budgets. Gravity can trade energy between bodies, but the trade rules are strict. When a route looks very tidy, the next question is not whether it looks like our plans. It is whether the turns it appears to take can be earned by the natural inheritance of a fast fly-through. If the same neat arc can be drawn by initial angle, and the small familiar forces of heating and venting, the tidy look loses some of its sting. If, after careful accounting, the arc still asks for precision that strains what those forces can buy, curiosity grows. Light curves then enter like witnesses who never agree perfectly. A strong, repeating rise and fall as the body rotates is the comfort food of small body science. It tells us that a simple shape is showing different faces to the sun. When the pattern refuses to settle, suspicion stirs. There are common reasons for a messy rhythm, a tumbling spin state that is not damped yet, a very irregular shape. A nucleus sheds fragments that drift close by and confuse the signal. Any of these can sculpt the glow into fans and shells and threads that the public reads as firing arcs. The check on our imagination is not to banish the idea of purpose. It is to see how far the ordinary can walk before we ask the extraordinary to take a step. Machine inference is helpful when it behaves like a colleague instead of a judge. If you ask a model to flag rare combinations of geometry and brightness behavior within its training set, it will hand you a shortlist. That list is a good place to spend human attention. It becomes a bad place to draw conclusions when the training set does not match the true mix of visitors, or when the question itself biases our expectations. Change the diet and the shortlist changes. Change the cost of false alarms compared to misses, and the flags move. The right way to use the label unusual is as a prompt to write down predictions instead of stories. Predictions are the boundary between mood and measurement. If a path is genuinely optimized for surveying several worlds, name which instruments near those worlds that can see what and when. If a blackout from Earth is part of a plan, name which other vantage should be favored and what it should see in that window. If the inner heating pattern is being adjusted by anything other than sunlight and rotation, name a behavior that should repeat cleanly even when the solar wind snaps and the magnetic field swings. The point is not to force drama into a test. The point is to make sure a test exists that can dispel drama honestly. There is one more angle that keeps this conversation fair. In a large enough sample, rare alignments are expected. If we keep records for decades, the catalogue of visitors will include more than one that threads enticing neighborhoods and more than one that hides in glare at a tantalizing moment. If the subset that looks optimized remains a handful, that is an advertisement for selection effects. If the subset grows and rhymes in ways that models cannot reproduce without help, the needle on the scale moves. That is not a refusal to answer today. It is an agreement to count tomorrow. None of this drains the thrill from a pretty curve. Sitting with a chart that seems to draw itself towards several theaters we know and love is part of why we watch. The discipline is to put the thrill to work. It pushes us to schedule attempts at angles that will either reward the efficient route story or erode it. It pushes us to publish the empty hands as quickly as the full ones. It pushes us to invest in viewpoints away from Earth so that solar glare stops being a plot twist and becomes just another line on the calendar. The curve, however, cannot tell us everything about nature versus intent. At some point, the question turns from where it goes to what it is. Composition and texture, dust and gas, heat and color are the parts of the script that we can read even when geometry teases us. If the shell behaves like ice and rock under a star, that tells its own kind of truth. If something inside is trying to steer through the weather we know, it will have to leave fingerprints in how the material breathes, which is the right set of clues to follow next, and how far can they take us before our metaphors outrun our spectra. Light is the courier we can trust at interstellar distances. Everything we say about what 3i Atlas is made of begins with light reflected from its surface and light emitted as it warms. Spread that light into colors, and a pattern appears. Some colors are missing because certain substances absorb them. Others glow a little brighter because grains scatter them well. For a United States audience used to weather maps and medical scans, think of a spectrum as a barcode. Each bar points to a family of materials rather than a single molecule, and the art is to read the families without pretending the scanner can name every ingredient on the receipt. Water ice is the familiar anchor in this language. When sunlight hits a surface mixed with ice, the near-infrared bands carry broad, shallow dips that say cold chemistry lives there. As the object comes within tens of millions of miles of the sun, that ice can turn straight to vapor. Vapor escapes. Dust rides along. A soft envelope called a coma forms around the nucleus. Under the continuous breeze of charged particles flowing from the sun, the coma stretches into tails. One tail is dominated by dust that sunlight pushes gently outward. Another is built from ions born when ultraviolet light strips electrons from gases. Dust speaks in broad colors. Ions speak in narrow lines. If our instruments are patient and the geometry is kind, we can hear both. Carbon compounds complicate and enrich the picture. Some are simple gases like carbon monoxide and carbon dioxide that switch on and off depending on temperature. Others are bigger organics locked in dust. In spect, they appear as rises and slopes rather than neat little spikes. That is enough to say carbon is in the mix and that the material has not been cooked to sterility. It is not enough to claim that specific prebiotic molecules have been measured. A careful script for an American audience makes that distinction clear. The families are consistent with ingredients that life later uses in other places. They are no proof that life has ever touched this one. Silicate minerals, the stuff of sand and many rocks, contribute at different wavelengths. They sketch a history of heating and shock. A surface that has been baked by many close passes around some other star looks different than a surface recently exposed by a crack. If we see a dominance of fresh-looking grains, it hints at the recent opening of vents. If we see signatures of glassy material, it hints at fast heating or impacts that melted and quenched dust. None of this requires exotic assumptions. It invites us to read the layers as pages in an old book that has been opened, shut, and opened again. Dust itself is a storyteller. Grain sizes shape what we see. Fine grains scatter blue light differently from red and make a coma look soft and bright. Larger grains carry momentum and stay closer to the path, adding weight to a tale that lingers. Polarization, the tendency for scattered light to line up its waves in certain directions, tells us about grain shape and texture. A fluffy cluster of tiny bits behaves differently from a compact pebble. Polarimetry is not a household word, but its meaning is friendly. It is asking whether the reflected light has a preferred handshake. From that handshake, we infer how rough or smooth the dust is, and whether it looks more like soot, snow, or ash. Heat completes the trio. A dark surface drinks sunlight and runs warm. A bright surface reflects more and stays cooler. If the surface has low thermal inertia, it warms quickly at dawn and cools quickly at dusk, which matters when the nucleus spins. If the surface stores heat, afternoon vents may run stronger than morning ones. Infrared instruments watch this dance. They do not need to resolve the nucleus as a disk. They only need the steady rise and fall of warmth to sketch a daily rhythm. That rhythm helps identify faces and patches that behave differently and anchors rotation when the optical light curve alone is too messy to solve. Put these pieces together and a biography starts to take shape. Somewhere around another star, far from heat, water, and carbon, froze onto dust. Grains clumped, clumps stuck. A small body formed, porous like packed snow. Later, the neighborhood changed. Newborn planets migrated. Gravitational scuffles ejected some bodies into the dark between stars. Our visitor carried a patchwork, frozen layers from a cold nursery, crusts cooked by sunlight during past flybys of its native sun, and scars from collisions that knocked loose fragments and exposed new surfaces. For ages it wandered. Cosmic rays darkened the skin. Thermal stress opened seams. Where seams opened, volatile pockets vented and then sealed again. This is the ordinary epic of small bodies. It is more than enough to explain the drama when sunlight returns. Outbursts live comfortably inside this frame. A sudden brightening need not be a message. It can be a cap of dust collapsing over a pocket of gas. It can be a slab turning a face to the sun that was dark a day earlier. It can be a small fragment breaking free and releasing fresh material that was hidden. To a public used to plots, an outburst looks like a signal. To instruments calibrated for patience, it looks like the weather is stirred by topography and heat. That does not drain the wonder. It steers the wonder toward what we can test. Size estimates belong in the same honest light. When a body is unresolved, brightness is our only clue. Brightness depends on diameter, reflectivity, and the way a shape presents itself. Change any of those, and the inferred size changes. A dark body covered in coarse dust can appear small when it is not. A bright, flaky surface can appear large when it is not. Early in the campaign, the right thing to tell a general audience is a range. As phase angles improve and thermal measurements accumulate, the range shrinks. If the range moves away from a number that made a headline feel exciting, the headline yields to the range. It is not a retreat, it is the point. Porosity is the quiet engine behind many of these behaviors. A porous nucleus acts like a sponge. Heat seeps unevenly. Gases percolate along tortuous paths. Vents turn on and off as channels clog and clear. Even a small change in spin can put a working vent into shadow or bring a dormant one into day. The coma responds like breath under exercise, sometimes calm, sometimes panting. The tails record those breaths as shells and fans that repeat roughly with rotation and vary with distance from the sun. Add the constant tug and twist of the solar wind, and the result is a canvas crowded with features that look planned to a mind hungry for plans. The cure is not cynicism. It is to name the natural paints first, what would truly strain a natural account. A thermal signature that stays hotter than conductive materials should allow at a given distance from the sun. Emission lines from metallic alloys that have no plausible geological pathway in this environment. Light curves that repeat with precision beyond what a tumbling shape, rotation, and patchy venting can produce. And that repeat even when solar weather should disturb them. A stable, narrowband radiotone that remains locked and indifferent to the surrounding plasma. Nobody expects these. If any appear with credible calibration, the center of gravity of the story moves, and the burden of proof flips. Until then, the catalogue of ordinary strangeness is deep. All this talk of chemistry and heat is not a lecture for its own sake. It is a schedule. Water-driven activity is likely to surge at certain distances from the sun. Plan your best infrared passes for those dates. If carbon monoxide tends to appear at cooler temperatures, schedule earlier. If polarimetry will separate fluffy dust from compact grains at a particular angle between the sun, object, and Earth, put that angle on the calendar and fight for it. For American observatories juggling many targets, this is the difference between catching data that breaks a stalemate and collecting pretty pictures that teach little. The reward is a timeline with before and after views that make sense as a pair. There is a cousin to chemical composition that interests anyone who wonders about concealment, and that is the texture of coverings. A designer who wants to hide a device inside a natural shell would choose materials and grain sizes that mimic known comets. The easier test for us is not to search for a single impossible substance, but to search for consistency that is a little too perfect. If a coma holds a symmetry through day and night, that normal spin and venting should break. Suspicion rises. If thermal behavior refuses to show the afternoon bias that low inertia materials almost always show, suspicion rises. If venting aligns again and again with conditions that favor coverage rather than with simple sunlight, suspicion rises. None of these alone settles anything. Together, if they survive solar wind and geometry, they press for a new layer of explanation. When it comes to machine learning, material clues are a better diet than orbital poetry. Train a system to separate spectra by families of substances and by how those families change with distance from the sun. Ask it to flag targets whose changes do not follow the common tracks. Use ground truth from well-studied comets to teach the model what normal looks like when data are sparse. Now, a label like unusual speaks to physics rather than to the thin coincidence of timing and vantage. It is still not a verdict. It is a sharpened prompt for where humans should look twice. There is a plain reason to keep the material story grounded. It is the one domain where our tools are strongest. A well-calibrated spectrograph in Arizona or Hawaii, or on a satellite, keeps its promises. A polarimeter turns noisy frames into a clean trend if you give it time. A thermal instrument tells you about heat even when the nucleus is a point. These are humble sensors compared to the imaginations chasing the sky. But humble wins a lot of races. If we teach the public to follow these curves as they rise and fall, a season of watching becomes a class in reading a living object, not a lottery ticket for a revelation. A word about outliers that refuse to be tamed. Every sample has a stubborn corner, and 3i Atlas may visit it. If a light curve remains chaotic after phase angles improve, it can be a true tumble or a procession of shedding fragments that never settles. If a composition looks skewed compared to comets we know, it can be a product of a colder nursery around another star. If dust grains show a bias in size that refuses to budge, it can be a clue to the way small bodies formed there. These are discoveries that stand on their own. They do not need a conspirator. They need a notebook and time. American viewers who have learned to love pictures of Saturn and the pillars of the Eagle Nebula can love a clean plot too, once they learn what it is saying. When public curiosity tilts toward the idea of a cloaked probe, composition still matters. A hidden core would want the outer layers to do the heavy lifting. It would lean on natural outgassing to mask any small adjustments of orientation or heat dumping. That means the outer layers must be ordinary enough to carry the show. If the show matches what dust and ice normally do, that does not prove there is nothing inside. It lowers the odds that anything inside has to act. If, on the other hand, the shell consistently behaves like a rehearsed costume, keeping features aligned through shocks and spins, the conversation changes. The ethical question that trailed behind that change is not a plot twist. It is a compass check. How do we respond if we think purpose is on the table? But the evidence is this. Do we act louder or measure longer? There is also a human reason to stay honest with materials. It gives teachers and creators a stable bridge to cross with their audiences. A parent in Ohio can explain to a child why the same object looks different when the sun is behind it and when the sun is off to the side. A student in California can compare two spectra from the same week and mark the tiny differences without knowing the names of every band. A local club in Texas can plot brightness night after night and see a period float into view as if out of fog. That is how a story that could have been swallowed by rumor becomes a shared craft. In the end, composition and heat tell you how a body breathes. They do not tell you how the surrounding air flows. That air, in space, is a river of charged particles. It drapes magnetic fields across the coma and sculpts tails into lances and ribbons. It can break a tail clean off and let it grow again. It can bend a narrow ion tail in directions that make observers think a pilot is nudging the wheel. If we want the material story to carry its proper weight, we must set it beside the plasma story and learn to read both at once. The next part steps into that river and asks what the sun's wind can and cannot explain when an interstellar traveler passes through our neighborhood. Space near the sun is not empty. It is a river of charged particles racing outward in all directions, a continuous wind made of electrons and ions that carries the sun's magnetic field the way a stream carries leaves. That wind fills the solar system. It threads space with the spiral of magnetism because the sun rotates while the wind flows. Any visitor that releases gas and dust into this river begins to speak a second language beyond gravity and light. It starts to write with electric and magnetic forces, and the script it writes can be misread by audiences who expect smooth arcs and quiet skies. A neutral atom leaving a sunlit surface lives a short, simple life. Ultraviolet light knocks away an electron. Charge exchange with the solar wind can do the same. Once ionized, the new particle feels the Lorentz force, a combination of electric and magnetic tugs that exists whenever a conducting fluid moves through a magnetic field. The ion begins to spiral around a field line. Meanwhile, the wind drags the entire ensemble outward, so the path is not a perfect circle, but a stretched corkscrew laid along the field. Multiply this by a cloud's worth of ions, and you have the beginnings of an ion tail, the thin lance that points away from the sun, regardless of the object's direction of travel. That tail hums with waves and ripples. It carries kinks and bends. It responds to shocks launched by the sun days earlier. To a plasma physicist, this is weather. To a newcomer, it can look like steering. Dust grains join the drama at their own pace. Sunlight charges them. Collisions with plasma adjust that charge. Charged grains drift in electric fields, while gravity and radiation pressure push from other directions. Small grains respond quickly, large grain lumber. The result is a dust tail that broadens and curves, its shape set by grain size, charge, and the way sunlight scatters from rough, tiny surfaces. Colors in photographs are not paint. They are physics, a record of how different sizes and charges respond to the same light and wind. The solar magnetic field never sits still. It ripples with turbulence from below the sun's surface and jerks when shocks from eruptions sweep past. When such a disturbance crosses a comet-like atmosphere, the field lines drape around the obstacle the way water wraps a rock in a stream. Upstream, the flow slows and heats. A boundary forms that acts like a shock, even though the nucleus has no built-in magnetic field of its own. Downstream, the field stretches into a tail that can twist, kink, and even snap free. When a strong disturbance triggers reconnection, the tail can disconnect, drift away, and grow again. A camera watching only the tail sees a structure vanish and reappear, as if on command. A camera watching the sun sees a shock arrive on schedule. Put the two together, and the command turns back into weather. Electric currents appear where no wires exist. As ions escape, charge separation arises, and fields respond to cancel it. That response is a current, and currents create magnetic fields. The result is an induced magnetosphere, a bubble where the plasma moves as if the object carried a magnet. Inside, flow slows and turns. At the boundary, shear between different speeds breeds waves and eddies. These structures modulate how gas escapes, which modulates how the atmosphere glows and how the tail looks in images. If the escape pattern rotates with the nucleus, the glow can pulse. If the flow is buffeted from outside, the glow can flicker. Translate either into a timeline, and it is easy to draw a straight line to intent when the true line runs through plasma and spin. Bright sodium emissions add a twist. Some comets grow a faint, narrow tail of neutral sodium atoms that scatter sunlight at specific colors. That tail behaves differently from ion tails and dust tails. It can appear and fade depending on exposure to sunlight and on the way grains release sodium. An observer who is not expecting multiple tails can mistake one for another, or can call a change a deliberate act when it is simply a switch between channels. Radio and ultraviolet ears hear more. Certain ions fluoresce when sunlight hits them, re-emitting at narrow wavelengths that spectrographs can isolate. Freshly born ions can also excite waves in the plasma as they are picked up and accelerated by the wind. Instruments record those waves as narrow features that can masquerade as engineered tones if context is missing. Even the arrival of a solar shock can change how radio waves travel through space, altering polarization or arrival time in ways that look sudden. These are diagnostics for patient teams and traps for stories told at speed. Geometry keeps doing its quiet work. The most important electric field in this environment is the motional field, a simple outcome of the wind flowing across the magnetic field. Change the angle between the visitor's path and the field, and the direction of this effective electric field changes too. Jets of ions bend differently. The ion tail swings. If you watch only the tail and not the upstream field, the swing looks like a pilot's hand on a control stick. If you watch both, the pilot becomes a breeze. This is why simultaneous measurements matter more than spectacular ones. A dull, steady record of the field can solve arguments that a week of striking images cannot resolve. Timing can mislead as easily as geometry. The sun's outbursts take time to reach different parts of the solar system. Monitors near the sun feel a shock first. Instruments near Earth feel it later. A visitor in between will feel it at their own time, depending on their position. If your cameras catch a tail event, and you later discover a solar eruption that could have caused it, the clocks might look wrong from one vantage and right from another. Unless you align all clocks to the path of the shock through space, you can dismiss the solar cause and reach for a more dramatic one. Coordinated timelines prevent this. They require teams to share not just pictures, but spacecraft ephemerides, data latencies, and timestamps with real uncertainties. Without that discipline, coincidence becomes content. Certain features remain stubborn even after you account for geometry, timing, and field direction. Narrow rays that shoot down the tail and fade. Concentric shells in the coma that repeat for several rotations. A clean periodicity that refuses to smear even when solar weather is active. These deserve attention because they test the edges of natural explanations. Many have natural accounts. Rays can be caustics, places where particle paths and viewing angles briefly superpose to create bright lanes. Shells can be the signature of a vent that activates whenever the same face warms. A clean period can be rotated, finally revealing itself after days of poor coverage. Every so often, a feature resists. That is when extraordinary claims must start paying rent by making extraordinary predictions. If a feature is driven by a repeating device, it should keep schedule regardless of space weather. If it is driven by the field, it should follow the field as it rotates with the spiral. If it is driven by rotation, it should stay tied to the light curve even when the tail bends. Promise these tests aloud before the data arrive, and then accept the outcome they deliver. What measurements tame this environment? The ones that are simultaneous and boring in the best way. Optical cameras track the coma and dust tail. Narrowband filters isolate key ions. Infrared eyes follow heat, showing when and where the surface energizes outgassing. Radio arrays listen for lines and for the faint signatures of waves excited by newborn ions. Magnetometers on Earth and in space build a picture of the wind and the field, both upstream and downstream. None of this requires a new kind of telescope or a secret algorithm. It requires the humility to say we need all of it at once if we want to separate weather from will. There are crisp, public-facing tests that turn plasma literacy into decisions. Watch for tail disconnections when a known shock is due. If the rate of disconnections spikes after shocks arrive, the solar weather account strengthens. Correlate the swing of the ion tail with the measured field direction at a nearby spacecraft. If the swings follow the field, intent retreats. Look for sudden, significant changes in the non-gravitational term of the orbit solution that do not align with solar events or with rotation phase, but with nothing else at all. Those would be rarer and more interesting. They would not by themselves prove steering. They would shrink the list of natural suspects and justify sharper scrutiny. American viewers often ask where the frontier is in a field that seems to speak a private language. Here, the frontier is not in discovering that plasma exists. It is in learning to read its handwriting at a moving target under time pressure. Every visitor teaches a slightly different pen stroke. Some pass during solar quiet when the wind is steady. Others arrive during active seasons when the wind is restless. The shapes of their tails, the pulses in their atmospheres, the way they respond to the spiral field, all of these add up to a catalogue that makes the next case easier to pass. That catalogue is the antidote to the illusion that every odd feature demands a pilot. It is also the foundation for recognizing a pilot if one ever appears, because you cannot spot a deviation until you have a dependable sense of the norm. There is also a human field that courses through this story. Teams work at night, under deadlines, while public interest surges and ebbs. A beautiful sequence of images tempts poetic captions. A jagged light curve tempts a plot twist. The best guardrail is preparation. Write down ahead of time what a plasma-driven event should look like across instruments when a shock arrives. Write down what a rotation-driven event should look like when the illumination angle shifts. Write down what a device-driven event would have to do to elude both. Then hold your own script to those promises when the data pours in. Machine learning has a useful role here if we feed it the right diet. Train on labeled cases where ion tails followed measured fields, where disconnections match known shocks, and where rotation signatures beat through flicker. Ask the model to flag cases that do not match any of those families. No, a label like unusual means unusual relative to known plasma behaviors, not simply unusual relative to a mixed bag of orbits and light curves. Even then, the label is a bookmark, not a verdict. It tells human teams where to look twice and where to spend precious pointing time. The practical payoffs of plasma literacy extend beyond this visitor. They help protect satellites and power grids during storms. By teaching forecasters how the wind moves through the system, they help mission designers decide when to schedule sensitive spacecraft operations. They turn a public story into a civics lesson about space weather that matters in everyday life, from radio blackouts to auroras over American states that do not often see them. When the same measurements build both a better forecast and a cleaner test for a sky mystery, everyone wins. None of these rules out a deeper layer. It clears underbrush. If someone hid a craft inside a natural shell and timed small nudges to avoid standing out, those nudges would need to hide inside the chaos of plasma. They would avoid moments when the tail is calm and the field is steady. They would choose moments when disconnections and swings are expected anyway. They would never ask a tail to do something the wind could not plausibly do. They would look like weather, until you notice that certain alignments keep repeating when they do not need to. That thought belongs to the next part, where we try on the engineering lens not to declare intent, but to outline how a hidden mission would have to behave to remain invisible in a world that is already noisy. So we have learned the river and its rules. We have seen how ions are born and carried, how dust is charged and sifted, how fields drape and reconnect, how tails swing, snap, and grow again. We have a set of tests that respect the wind before they invoke a hand. With that foundation, the next question becomes sharper. If purpose did ride inside a natural shell, what would it want? How would it power and cool itself? When would it speak? And why would the sun's bright curtain be the place to do it? Start with restraint. A surveyor who wants to pass through a busy planetary system without sparking alarms would choose a costume our instruments already understand. In our sky, the least suspicious outfit is a dark, irregular nucleus that breathes dust and gas as sunlight warms it, leaving a soft halo and a tail that 1,000 telescopes have seen before. The disguise is not only about looks, it is about behavior. The track honors gravity. Brightening and fading keep pace with distance from the sun. The tails answer to space weather. Nothing in the outer show requires thrust. If there is a machine, it sits inside and lets physics carry the performance. What purpose would justify such caution? A single pass can harvest a catalogue that has taken us generations to build with many spacecraft. Map the plasma and magnetic environment of the inner solar system at longitudes our probes rarely cross. Sample dust populations in lanes that satellites and stations occupy. Study atmospheres, rings, and magnetospheres at slanted angles that are hard for us to schedule. Record the radio murmur of our planet and our hardware to gauge how loud a young technological species sounds against the hiss of the sun. Watch how a life-bearing world glows in thermal bands as day turns to night, gathering lessons for exoplanet work elsewhere. Note how our networks respond to unusual events and infer our detection thresholds. None of that requires contact. All of it benefits from a route that glides near several theaters without parking at any of them. The path would borrow the same playbook our navigators use. An inbound trajectory with interstellar speed leaves little room for braking. Instead of slowing, the craft trims direction through carefully chosen passes. Skimming far ahead of a planet bends the track outward. Skimming far behind bends it sunward. The sun itself is a tool. A close swing near the star multiplies the effect of any minor nudge. The way a small turn of the wrist near the hub of a wheel pivots the rim. The bright weeks around the turn offer a curtain. If you plan decades, you can time deployments and data transfers for moments when Earth sits at poor angles and cameras must be cautious. Power for the hidden core has to be quiet. Solar arrays would be safest, but panels flashing in sunlight would betray the ruse. One answer is to hide small collectors beneath sacrificial layers that flake away only when geometry guarantees invisibility. Another is to store energy chemically and spend it in bursts. Either way, the waste heat must be bled in ways that mimic natural warming. A smart core changes its orientation so that radiators vent heat toward regions of the shell already active. To an outside observer, the extra warmth blends into a pattern caused by sunlight alone. The same trick works for internal housekeeping. Any moving panel or aperture shifts when the coma is thickest, or when a known solar disturbance is due. The signal drowns in the weather. Sensing can be almost entirely passive. Narrow and wide cameras peering through small tunnels in the shell. Infrared eyes that measure temperature changes in the atmosphere and on surfaces. Magnetometers that sit on a short boom and measure the dip of the solar field. Plasma cups that count ions and electrons as they wash past. Dust counters that tally grain sizes and speeds at a safe offset from the core. Radio receivers that listen across bands used by communications and radar, not to decode, but to map density and reach. All of it is mounted behind replaceable filters or charge grids that clear clinging grains by reversing polarity, the way some terrestrial instruments keep lenses free of dust. The hallmark is patience. The core collects more than it transmits, saving the loudest act for a time when glare and geometry make eavesdropping on the transmission hard. Communication favors long integrations over loud beacons. A tight, faint beam to a relay that sits far from the orbital plane can ferry data at low rates for months. The relay might be nothing more than a quiet receiver parked well outside our traffic lanes. Another strategy is to hold the entire archive until after the solar turn, and then transmit while Earth is badly placed, trading days of invisibility for months of safety. A culture that values caution would accept latency rather than risk discovery by a strong, short burst. Propulsion is the most revealing choice. Any obvious jet would stand out. A hidden core would steer by timing and by thermal discipline. Small reaction wheels or moving masses inside the shell can change the orientation of the nucleus slowly. Change the orientation, and you change which patches of shell warm and when they vent. Gas escaping from a sunlit face pushes gently against the core in the opposite direction. Over many hours, those nudges add up to a measurable tweak that hides within the messy family of non-gravitational forces that comet specialists already model. No flash, no plume, just a drift that could pass for uneven heating on a lumpy surface. Release of subcraft is the riskiest maneuver, and therefore the one most likely to hide behind the sun. If the mission needs tiny scouts to peel away, they separate when Earth is buried in glare. They do not sprint. They loiter near the parent on similar tracks, then fall into slightly different lanes that take them past targets of interest. Their surfaces are dark and textured. Their instruments are passive. Their lives are measured in days. They either transmit toward a high-latitude relay the moment geometry allows, or they cache packages for pickup on the outbound leg. If one fails and is noticed, it looks like debris from the natural shell, another fragment in a familiar fog. Signature management is less about erasing traces than about matching expectations. Our instruments expect comas to swell with heat, tails to bend with the spiral field, and light curves to wobble with rotation and shape. A careful designer leans into those patterns. If an aperture must open, it opens when the tail is already in turmoil from a solar shock. If a radiator must dump heat, it dumps when the face is sunward and vents are on anyway. If a sensor must stare, it stares through channels carved well ahead of time, so the line of sight stays clear while the outer fog shifts. The task is not invisibility. It is plausible deniability at every timescale we can measure. Could such a core survive the violence near the Sioux? Materials and structure make the difference. The shell can be sintered dust and volatile ices, engineered to crack in a forgiving way, rather than splinter into shards. Thin sacrificial skins protect instrument windows and peel away in layers. Whipple-style shielding stands between the core and hypervelocity dust, turning a single dangerous grain into a harmless bloom of fragments before it reaches the main wall. Internally, vibration isolators ride out the worst of the heating and cooling cycles. None of this is fantastic. It is the logical extension of how we already protect our own probes. How would we catch it cheating? Not by hunting for a single impossible substance, but by looking for consistency that is too good to be natural. Comas that stay symmetric through changing sunlight and known shocks. Light curves that hold a clockwork period, with a sharpness hard to reconcile with rough shapes and vent flicker. Thermal behavior that refuses to show the afternoon bias common to low inertia surfaces. Repeated alignment between tail features, and convenient geometry when the sun and the wind would predict otherwise. Each sign alone can be explained. A stubborn cluster that persists across viewing angles and solar moods begins to earn attention. Why choose concealment at all? We can tell a dozen stories, none of which require menace. A mature culture might bind itself to first contact rules that err on the side of non-interference. A quiet pass allows study of a biosphere and a technological network before presence changes the picture. The sun itself could be the main laboratory, with our planets an incidental benefit. Or the route could be mapping safe lanes for traffic in a heliosphere that bristles with hardware and storms. Silence is not always an insult. Often it is protocol. There is an ethics on our side too. If evidence piles up toward a purpose without crossing the threshold most of us would require, what do? Announcing more than we can prove burns trust. Announcing less than our best inference burns courage. The compromise is old and sturdy. Write down the near-term tests and publish both hits and misses on the schedule you promised. Keep the language concrete. Invite independent checks by sharing the raw frames and the processing steps. Build observing plans that would embarrass any claim that dodges a fair test. If the purpose is there, it will survive public scrutiny. There is a positive way to put this engineering lens to work, even if it never finds a culprit. Treat it as a generator of predictions for ordinary physics. If a disguised craft were to time its gentle adjustments to coincide with natural outgassing, look for correlations between tiny orbital drifts and surface patches that appear to wake and sleep. If it would prefer to move during space weather, look for clusters of changes near known shocks. If it avoids narrowband emissions, expect an absence of stubborn, unexplained lines and a prevalence of broadband features. These expectations are dull compared to headlines. They are also measurable. They improve our models, whether or not a secret machine exists. For an American audience that wants to participate rather than only watch, there are roles here that match backyard tools. High-cadence photometry from small telescopes can catch periods and flicker that big mirrors do not have time to chase. Coordinated imaging with polarizing filters can map how dust grains change day by day. Citizen radio groups can monitor quiet bands for iron-related features and post timelines that professionals can cross-reference. The point is not to crowdsource a revelation, it is to knit a network that makes any claim, exciting or sober, live or die by shared clocks. At the end of this exercise, the disguise does not dissolve. It either holds or it frays. If it holds, we still win, because the tests leave us with cleaner catalogues of what comets and their cousins do under stress. If it frays, we still win, because the same catalogues give us the baseline against which anything deliberate must stand out. A pilot cannot fake the wind forever. Eventually, patterns cross at angles that the river cannot sustain. All of these points forward to a very human choice. Waiting for luck is not a plan. If we want answers faster than chance delivers them, we need a mission that can leave Earth quickly, dive toward the sun for speed, and meet a fast stranger on its own terms. Interception does not promise certainty, but it converts rumor into measurements no telescope on Earth can make. What would such a mission look like? How would it fly? What instruments would earn their seat? And how do we prepare now so that when the next alert lights up our screens, we are ready to go rather than ready to wish? When a fast stranger is announced, the first wave is not romance. It is logistics. A notice drops from a survey pipeline with coordinates, a brightness estimate, and a stamp of uncertainty. Inside an hour, the message hops through email lists and Slack rooms that bind observatories, universities, and amateur networks into a loose web. People in Arizona look before dusk. People in Chile pick up after midnight. Someone in Hawaii bridges the gap. A smudge on a stacked frame turns into a clean point with a timestamp. 1 point becomes 2, then 10. Each addition tightens the leash on the predicted path and redraws a handful of boxes on a shared calendar. The boxes are not just nights. They are angles when a specific instrument can actually teach something instead of painting a pretty scene. Time is the first bottleneck. Large telescopes are scheduled months ahead. A few keep emergency slots for sudden targets, but those slots evaporate when the world pays attention. That is why well-run campaigns live by playbooks written long before the alert. A good playbook names who can trigger an override, which instruments can be retasked without unraveling other programs, which exposures and filters are minimum viable science, and how long a rapid sequence may hold the floor before the telescope returns to its cue. It also names what not to do. Do not chase glamour angles that tell you little. Do not burn twilight chasing a tale you cannot resolve. Do not risk a mirror or a detector by pointing too near the sun to feed a headline. Translation is the second bottleneck. Radar teams speak in power budgets and round-trip times. Optical teams speak in seeing and cadence. Radio arrays speak in baselines and bands. If each group transmits only in its dialect, the mosaic never forms. The fix is dull and essential, a living schedule that maps who is watching, at what angles, toward what goals, with what products promised when. Goals here are verbs, not nouns. Map a daily rhythm in heat. Sample dust polarization at 2-phase angles. Catch a tail disconnection within 3 hours of a solar shock passing a monitor. A Midwestern campus telescope, limited by aperture but blessed with clear skies, can fill a crucial hole if the verb fits. A small group with a narrowband filter can win the day if they hold a cadence the big mirrors cannot afford. Bias is the third, and it arrives dressed as excitement. Once a narrative takes hold, this looks like a tour. This window will be crucial attention skews. Data sets that confirm the feeling travel fast. Nulls go quiet. The cure is to pre-register simple expectations before the window opens. If the ion tail should follow the direction of the upstream field, write the threshold that counts as agreement and the threshold that would surprise you. If a light curve period is likely, write the tolerance that would make you call it real. Publish these notes, then print the miss as quickly as the hit. This is not bureaucracy. It is a habit that prevents a rumor from hardening into law while the data are still warm. Pipelines make or break early nights. Raw frames are numbers with ghosts, hot pixels, scattered light, internal reflections. Spectra carry skylines and instrument fingerprints. Teams with hardened pipelines can turn a night's worth of frames into a clean product before breakfast. Teams without them can turn the same night into noise and doubt. The healthy pattern is redundancy. One reference pipeline is maintained by a small consortium and posted in the open. A second, independent pipeline that replicates the critical steps and names every difference. When the two agree, confidence rises. When they diverge, the notebooks tell you why. The public rarely reads those notebooks. They will feel the difference when updates from different groups rhyme instead of fighting. Space weather must be treated as a co-author, not as background. The sun throws shocks, streams, and turbulence into the heliosphere on its own schedule. Those disturbances reach different places at different times. A kink in a tale without a space weather timeline is an invitation to myth. A kink laid beside the record from monitors near the sun, monitors near Earth, and models that trace the shock through space becomes a test. The field learns to say, "We expect an effect tonight," or "We do not expect one," instead of "We will see what we see." That one habit collapses a dozen conspiracy threads before they hatch. Borders both hinder and help. Power cuts in one country do not silence another. Winter clouds in one hemisphere are summer skies in another. A telescope that cannot risk the sun's brightness hands the baton to a deep space probe with a different geometry. None of that happens by goodwill alone. It happens because people signed memoranda in quiet months that grant emergency overrides, mirror data in neutral repositories, and route heavy downloads to centers that can carry them. It happens because teams rehearse. A dry run in September, where a fake alert triggers real motion, will find the busted link in a matter of hours. Repairing the link takes longer. You want to discover the break before a real visitor does. Amateurs are not a garnish. They are an organ. Backyard telescopes, when disciplined, can outpace a big dome on cadence and sky coverage. 1,000 small rigs, each contributing a handful of calibrated frames through agreed filters, can provide a light curve with gaps so small that rotation, if it exists, floats into view. A coordinator posts nightly parameters, a template for reporting, and a place to upload. A small review team vets and merges. Credit is tracked in the open, so a high schooler in Ohio sees their initials on a figure that matters to someone flying a satellite. The result is not a substitute for heavy gear. It is a mesh that catches small truths that otherwise leak through. Media is a system too. With failure modes you can map. Vague words like close and aligned mean one thing to the lab and another to the living room. Close can mean tens of millions of miles. Intimate for instruments and a universe away for humans. Aligned can mean in the same patch of sky, not aimed. Good campaigns write distances with units, angles with dates, and avoid promising a thunderclap on a specific Thursday. They adopt a layered cadence, a daily paragraph in plain language, a short explainer on one concept that will matter tomorrow, and a less frequent long read that absorbs recurring questions. They also carry 3 artifacts that never move: a master timeline with absolute times, a glossary with definitions that don't drift, and a single chart that tracks the core orbital quantities as ranges, not razor lines. These quiet anchors do more than 100 tweeted corrections. Because artificial intelligence is now part of the public's mental furniture, we have to place it carefully. A model trained on catalogued orbits and light curves can flag unusual tracks. That word is useful if we remember what was fed to the model and what question it was asked. A catalogue heavy with bound comets will make any interstellar path glow red. A training diet that includes simulated visitors with varied speeds and angles changes the heat map. The right way to use such flags is to drive attention and telescope time to places where a human can decide, not to frame the flag as a finish line. And when a model is used, we should say so out loud. We should also say how its judgment might change if the training set or the cost of false alarms were different. It's not hedging, it's respect for the limits of pattern machines. Let's run a dry, concrete scenario, the kind that makes or breaks a campaign. The alert fires on a Monday before dawn on the East Coast. A coordinator posts coordinates and a one-page plan by breakfast. Narrowband ions tonight in the southwest. Thermal measurements tomorrow from a satellite window. High-cadence broadband from small scopes nightly through Friday. And a call for polarimetry on Saturday when the phase angle turns favorable. A space weather lead notes a shock that left the sun on Sunday and forecasts its arrival near the object on Wednesday afternoon, plus or minus 6 hours. The plan marks a watch window and asks 2 teams to sit on a tail disconnection attempt that evening. A media liaison prepares a daily note that says exactly this. Tonight is about ions. If a kink appears tomorrow night, it will likely be solar. If it does not, we will say so, and we will look harder at rotation. No promises, only chores with clocks. By Thursday, either the disconnection coincided with the shock, which strengthens the weather account, or it did not, which justifies a rarer line of questions. Either way, the public saw the test arrive and land when we said it would. Now imagine the opposite pattern. No plan. Overlapping requests stampede an overbooked telescope. A strong image is posted without its time or its filter. A viral clip is a simulation without a label. A sudden kink in the tail is paired with an ominous caption, and only days later does someone point out a solar shock that matches the time. Trust erodes. The next sober update looks like a walkback, even if it is the first serious thing anyone said. The physics did not change. The culture around it failed to pull together. Data rights and openness can either stabilize or poison the well. Raw frames dumped without calibration invite mischief. A long embargo invites rumors. The compromise is simple. Rapid release of calibrated products for a subset of key measurements with credit tied to use, and a slower, curated stream for the rest with clear dates and reasons. Credit is tracked like a ledger. If a small college's polarimetry carries a big conclusion, they stand as co-authors. When a major facility misses a window, the record shows the miss. That ledger looks unromantic. It is also why the next campaign will have more hands ready to help. Errors will happen. A telescope will deliver a ghost that looks like a jet. A radio line will be a local interference source. A plot will be labeled with the wrong axis. The rule that protects the whole system is contrition at speed. A correction should travel the same routes and with the same energy as the original mistake. Don't bury it in a footnote. Put it in the feed and on the nightly note. People do not punish honesty. They punish the sense that someone hopes to edit the record quietly. Policy and funding loom larger than many admit. Agencies can either force improvisation every season or seed readiness that looks boring until a crisis. Standing budgets for rapid targets of opportunity, shared ground stations, and open pipelines cost less than a single spectacular rescue mission and pay out across fields. Legislators do not need to learn magnetohydrodynamics to help. They need to hear a simple pledge from scientists. A null result announced on time is a win if it closes a door cleanly. When funders reward that pledge, campaigns become steadier, and the public's appetite for cliffhangers softens into an appetite for craft. There is a role here for classrooms that goes beyond watching a live stream. A teacher can turn a nightly light curve into a lab, plot brightness, fit a period, compare with a second school 2 time zones west, Students who have touched their own noisy data will not be seduced by a mislabeled simulation next time. They will ask for units. They will check axes. They will understand what it means when a team says the error bars shrank. In the end, coordination is a technology. It can be engineered, audited, and upgraded. It has failure modes you can list and patch. It becomes brittle if it belongs to one lab or one country. It becomes resilient if everyone owns a small piece of the apparatus time on a scope, a quiet valley for radio, a shared calendar, a server that never sleeps. The next fast visitor will measure the health of that apparatus as surely as it will test our theories. If we do the quiet work now, the season of watching will feel less like surfing a rumor and more like participating in a study. All of this organization builds toward a single practical act, deciding that wonder is not enough. If we want answers that photographs cannot give, we have to meet a traveler on its own terms. That means a vehicle, a trajectory, instruments that can taste dust at speed and read heat in a single breath, and a communications plan that brings the haul home over weeks. What does that mission look like? How fast must it fly? How do we practice before the lock turns in the sky? And what do we count as success if the grand mystery stays coy, even as the data pour in? A plan begins with a premise that refuses to budge. If a stranger from another star will not slow down for us, we must meet it at speed, take everything we can in a single breath, and bring the breath home intact. That premise runs through every other choice. It sets how fast we must fly, how hot we can afford to get, how much we can carry, and how long we can wait before we light the first stage. The gulf between a whiteboard and a launch pad is wide, but it narrows when you translate wonder into the plain currencies of trajectory, thermal margin, data rate, and schedule. Speed comes first because speed sets the table. Visitors that arrive on hyperbolic tracks carry excess velocity that the sun cannot soak up. We will not sidle alongside and say hello. We will dive, turn hard near the sun to buy velocity from the depth of the gravity well, and then sprint outward to cross the stranger's lane, at a geometry that yields the richest science for the least punishment. That turn near the sun is not a flourish. It multiplies whatever delta V the final stage can add in the hot minutes around perihelion. The price is heat. Shields must hold shape and emissivity under sunlight stronger than what our routine missions see. Coatings must not flake into our own fields of view. Harnesses, booms, and apertures must accept thermal gradients that would make conservative engineers reach for brakes. If we mean to lead, we build hardware that can stand this furnace and still look through it with clear eyes. The path into that furnace is written in encounters, from Earth to Venus or Earth to Earth, then inward, then into the hot turn, then out. Each gravity assist is a bend, bought with calendar time. The more bends you stack, the more time you spend. Time matters in two ways at once. You need it to set up the solar turn, and you cannot spend so much that the visitor has come and gone by the time you are ready. This is why a standing capability beats a scramble. A bus rated for hot perihelion work, a heat shield that has seen the chamber 100 times, an upper stage that can coast, relight, and coast again without drama, and an instrument suite that snaps into standard slots without making a new qualification matrix for every connector. These are the boring, essential pieces that turn an alert into a go. Propulsion choices decide what counts as feasible. Chemical stages deliver high thrust quickly. They are simple, proven, and well understood. They also run dry fast. Solar electric thrusters add speed by sipping propellant for months, trading time for delta V. They can spiral inward efficiently and line up the hot pass with the patience a chemical stage cannot afford. Nuclear thermal rockets promise an intoxicating blend of thrust and efficiency, shrinking calendars and opening trajectories that were daydreams a decade ago. They also demand a consensus about risk and policy that moves more slowly than the sky. Solar sails, romantic and elegant, ask for square miles of flawless film. They belong in a second-generation playbook, not the first. Unless we choose to treat the first mission as a sail demonstrator, and accept that the intercept may be a teaching moment rather than a full science harvest. Instruments are the honest core of the promise. If we accept that the default encounter is a fast flyby, then every box and aperture must pay its way under brutal conditions. Think of a tiered set, a narrow-angle camera with a shutter and detector designed for rapid exposures without smear to catch the nucleus and the throat of any jets, a wide-angle camera that never loses the coma and the tail during the violent minute around closest approach, an infrared spectrometer that reads temperature and composition across the shell of dust and gas and over the face of the nucleus, a mass spectrometer and a dust analyzer that tastes the environment directly, with baffles shaped by hypervelocity tests and inlets that can shrug off a brief sandstorm, a magnetometer on a boom long enough to escape the spacecraft's own whisper, and a plasma suite that can count ions and electrons while the rest of the vehicle is rattling, a radio and plasma wave receiver that hears faint emissions and the hiss of newborn ions being picked up by the wind. And one more, a robust, simple imager aimed at the sun to monitor the wind and field from the vehicle's own position, because context is not a luxury when a minute can rewrite the record. Shielding and pointing are not accessories, they define survival. Whipple shields, a thin, sacrificial bumper that shatters incoming grains before they strike a thicker wall, turn a lethal hit into a shower of slowing fragments. The geometry, spacing, and materials of those bumpers must be tuned to the grain sizes the mission expects, with an argument for the grains we misjudge. Between shields, sensitive volumes live on mounts that can tolerate shock without ringing for seconds. Pointing logic must straddle two imperatives that fight each other: keep instruments on target and keep the antenna talking. In practice, the craft spends the last hours before closest approach in a mode that prioritizes measurement, firing off short, opportunistic bursts of data to Earth whenever the antenna can walk near the line without stealing time from sensors. The confidence to live with such a mode comes from rehearsal. Fault protection cannot default to safe mode if a star tracker blanks out under a spray of bright coma. There will be no time to wait for the ground. The vehicle must ride through glitches the way a pilot rides through turbulence. Eyes forward, instruments steady, power to the wings. Navigation at these speeds is a separate mission hidden inside the first. The target you are aiming for is not a clean dot. It is a point buried in a glowing cloud, seen from a moving platform that is also being shoved by the sun's light and wind. Star trackers can saturate. Landmark tracking is impossible. The solution lives in layers. Ground-based astrometry, fed by the campaign you ran before launch, keeps the track honest. A bright coma centroid guides the last hours, with models trained on other comets helping the software avoid being pulled off by asymmetric jets. Onboard cameras compare the motion of faint tail structures between frames to refine the approach vector in the final minutes. None of these tricks is perfect. Together, they shape a pass that keeps the nucleus on the sensor long enough to fill the drives with data worth the years. Data, not images, will decide whether the mission was worth it. The raw rate during the sprint will exceed what you can downlink in real time by orders of magnitude. Compression helps, but not enough. The design answer is storage and patience. Solid-state recorders keep everything at full fidelity. After the pass, the vehicle turns into a courier, dribbling the archive back over weeks or months. That demands a high-gain antenna that can hold a tight beam, a low-gain backup for bad days, and transmitter power that does not cook your own thermal budget. It also demands ground time, the deep space network and partner dishes booked for a long, quiet campaign instead of 2 glorious nights. Your schedule is a ledger. Every hour on a dish is time you persuaded someone to give you by promising measured payoffs rather than fireworks. Policy and programmatics decide whether the ledger exists at all. A nation that wants to lead on this frontier treats readiness as infrastructure. It carries a flight-rated heat shield into the next fiscal year. It funds a hot environment bus as a product, not a one-off. It keeps a shelf of pre-qualified instruments that can ride when the alert comes, with modest variations in grating choices and filter sets that accommodate a range of plausible targets. It sets criteria in advance for when a trigger becomes a launch, so that politics does not decide whether a trajectory is good enough. It publishes those criteria so the public sees the moment a go becomes possible and the reasons a no remains wise. There is room for a two-vehicle architecture that fits American strengths. A flagship makes the hot turn, carries the heavy shield, and collects the core set of images, spectra, fields, and particles. A small daughter craft rides along and peels away hours or a day before the encounter, dropping into a slightly offset path that trades proximity for a different look angle. The small craft is cheap enough to be brave. It can fly deeper into dust than the parent dares. It can stare where the parent must blink. If it fails, the mission still succeeds. If it works, the pair gives you stereo across a moving, breathing target at a speed that gave previous generations only a flat page. Practice is not a slogan. It is a mission to a proxy. Before you gamble your reputation on an interstellar sprint, you throw the bus at a brutally fast long-period comet that comes screaming in from the outer dark. You run the same piloting logic, the same shield geometry, the same data mode. You discover that a connector you trusted shakes loose when the heat pulse runs through the structure. You learn that your star tracker needs a software patch to recognize fields swamped by moving dust. You find that your plan for antenna geometry conflicts with your plan for magnetometer quiet. You fix it when the stakes are measured in hurt pride, not in a one-shot headline. Interception geometry is not decoration. It drives what you can claim when you come home. A head-on cross gives you a lightning-quick look at the upstream face of the nucleus and the rawest taste of newborn ions and dust. It also multiplies risk. A trailing cross lowers relative speed and buys you seconds that feel like minutes in instrument time, at the cost of a heavier trajectory and a narrower launch window. A flank pass gives you a broadside view of the coma and tail that delights modelers and infuriates anyone who wanted a portrait of the nucleus. There is no right answer in the abstract. There is only the geometry your launch period, your bus, your shield, and your best science argument can support without lying to one another. Public expectations can make or break the return. If you sell a revelation, you invite disappointment even when the data are exquisite. If you sell a harvest, you teach patience. A good harvest script names specific measurements that will matter whether or not the central mystery tilts one way or the other. Grain size distributions across phase angles tell you how small bodies feed their tails under a star like ours. Thermal rhythms under violent heating tell you about porosity and texture in a regime we rarely sample. Ion pickup signatures under different field angles teach us heliophysics that we reuse for other missions and for space weather forecasting that keeps satellites and grids safe at home. These are not consolation prizes. They are the very reasons you built the craft in the first place. Costs are real, and American viewers expect plain talk about them. The first of anything is expensive. Heat shields that laugh at near-sun work will not be cheap. Booms and brackets that keep their strength under cycling loads will not be cheap. A pair of deep space dishes booked for months will not be cheap. But cost is sticky in both directions. It goes up when you reinvent, down when you reuse. A program that carries forward a hot bus, that builds a second and third copy of a proven shield, that qualifies a family of instruments rather than one, will bend the curve. Partnerships do more than share the bill. They share ground stations, spare slots in schedules, and talent pools that have learned how to stand the long night without turning every status check into a melodrama. There is a place in this architecture for genuine risk, named as such. A tiny ride-along that tests a chip-scale solar sail, deployed for minutes during the hot turn, and watched by the parent like a parent watches a child's first steps. A fast, expendable dust sampler that shoots a needle path across the densest part of the coma and returns a handful of grains to a catcher on the main craft. A narrowband radio whisper beamed at the ion tail to measure dispersion, not to talk to anyone, but to teach us how such signals travel through a living plasma at speed. These are not stunts bolted on for spice. They are the bridges to rendezvous missions a generation from now. If we take this step, we should also build a culture that dignifies what we bring back. That means writing the archive into the plan at the very beginning. Raw data go to a public vault after a short, defined period. Calibrated products follow a clock. Software for pipelines ships with the data. Credits ride with files. Teams that request months of exclusive time must say why and must say how the wider community will be paid back. None of that looks like a launch. All of it looks like leadership. Set against these practicalities is the rhythm of the sky. Alerts come when they come. Most will not match our best windows. Some will. Between them, the public will ask whether the coincidences that caught our imagination were coincidences at all. A mission will not settle that question by decree. It will settle it by gathering the kind of evidence that weakens stories that thrive on hints and strengthens stories that thrive on measurements. We do not have to promise more. We do have to promise that when the next chance appears, we will be ready to trade a season of rumor for a stack of plots that will still teach in 10 years. Which brings us to the oldest clock of all, the one that ticked long before we learned to count. We will build what we can in the years we have. The visitors will keep their own time. When their paths brush ours in ways that stir our taste for meaning, we will feel the tug again. Is it a chance? Is it a choice? The answer lives as much in the way we think about time and pattern as in any single pass through sunlight, and that is the terrain we step into next. Stand a human lifetime next to a star's calendar, and the scale mismatch is almost comic. We count in school years, elections, mortgage terms, and anniversaries. A comet or an interstellar shard counts in long winters and brief summers under many suns, then drifts for spans that would swallow our entire written record. When a traveler like 3I Atlas brushes our orbit, it is natural to press our small clock against its vast one and listen for a click that sounds like fate. If the closest sweep near the sun arrives just when Earth's vantage is worst, we call it suspicious timing. If the path threads near more than one planetary neighborhood, we call it a tour. If a learning system tags the pattern as unusual, the tag sticks to our imagination like a note on a map. Here be intention. This is how minds work. The art is not to fight that pull, but to harness it without letting it drive the cart. Begin with the way chance feels from the inside. Americans know the texture of a sports streak. A batter who sees everything as a beach ball for a week. A quarterback whose passes find hands as if guided. Afterward, commentators pick turning points. Beforehand, nobody could name the exact run. The same split between before and after lives in the sky. Before a visitor appears, the menu of possible paths is enormous. Afterward, we forget every path that did not happen and dwell on the one that did, as if the universe had foreshadowed it. That is not a scolding, it is a caution. Our memory carves highlights into inevitabilities. Good science asks how many non-highlights were possible, and how often highlights should show up by accident when you watch long enough. A second caution hides in the denominator we do not see. We meet the visitors that geometry and our instruments allow. We miss the ones that pass in daylight or behind the sun, or simply too faint for our surveys until it is too late to care. In daily life, the unseen denominator is obvious. You notice the one car with your hometown's license plate on a cross-country drive, but forget the thousands that were not from there. In astronomy, the denominator needs to be built deliberately. How many interstellar paths would have looked intriguing if only we had watched that part of the sky at the right hour? How many would have lined up with a planet in a way that seems meaningful, but would have been invisible to our cameras? Until we count the missing cases, our sense of rarity is a mood, not a measure. Deep time then tilts the table a second way. We like to lace celestial dates with human milestones. A visitor's long inward drift is paired with our inventions and discoveries, and the overlap feels like a chord. Our species learned to plant cities, to build radios, to leave boot prints on another world. And here, within the same grand chapter, comes a third interstellar object, stealing into the inner system and bowing near the sun when our view is worst. That parallel warms the heart and narrows the mind at once. The heart is right to feel wonder. The mind should remember how many centuries our timeline does not include, how many revolutions around our star passed without a telescope to notice any of it, and how many wanderers have likely traced forgettable lines through our nights without ever seeing their names in print. We also load words with more meaning than they can carry. Aligned sounds like aimed, close sounds like imminent, unusual sounds like forbidden. For a viewer in Denver or Atlanta, close might still mean tens of millions of miles, a gulf that swallows the moon's orbit many times over. Aligned can mean nothing more than the object and the sun sharing a small angle in the sky, a geometry problem rather than a gesture. Unusual inside an algorithm can mean simply that the training diet did not contain many cases like this, not that the sky is doing something it has sworn never to do. These words are not wrong. They are careless if we let them stand alone. A fairer way to hold coincidence is to turn it into a prediction instead of a feeling. If the route is truly efficient in the way a surveyor would choose, instruments near specific planets should catch transient signatures. At times our geometry predicts. If the blackout during perihelion is part of a plan to hide, then other vantage points should become unusually rich at that same moment. If a small, steady force other than heat and sunlight is steering the track, then the tiny deviations in the orbit should repeat with a rhythm that ignores solar disturbances and viewing angle. These are not dramatic declarations. They are chores with clocks. The difference matters. Feelings cannot be disproved. Predictions can disappoint, and disappointment is how we learn. There is a quieter, mathematical discomfort that deserves plain English. Small uncertainties at the start grow large when you push models far into the past or the future. This is not chaos in the cinematic sense. It is humility. The farther you roll an orbit backward to ask when a visitor first passed through the outskirts of our system, the wider the date range becomes, until the range is larger than the human episodes we are tempted to pair with it. We can say a traveler entered the far reaches long ago. We cannot put it on the same calendar as cities, alphabets, or radio without painting the edges of the numbers. The right mood is not shyness. It is honesty about fuzziness before we fuse fuzziness with myth. There is also our bias toward peaks. We remember the most photogenic frames. We quote the strangest sentences. We share the graphs that make our favorite story look crisp. Whole shelves of data that show nothing peculiar sit quietly in archives, ready to be consulted, but rarely asked onto the stage. This is not malice. It is how attention works. The cure is institutional, not personal. Agree in advance that a handful of keystone measurements will be published on schedule, whether or not they show what any camp hopes to see. That way, the public learns that silence can mean no effect rather than conspiracy, and that a clean null is not a cop-out, but a brick in a wall we are all trying to raise. The way we narrate uncertainty shapes what we do when the next alert arrives. Treat coincidences as destiny, and you may chase tests that are theatre. Treat coincidences as noise, and you may ignore the one signal that deserves a closer ear. The middle path is practical. Write down before the window opens what would count as a surprise and what would count as a yawn. If an ion tail swings with the measured direction of the solar magnetic field, call it ordinary and move on. If it holds itself stiff against those swings through several field rotations, circle that date in red and invite colleagues to take their shots. This is not a hedge. It is a way to give both skepticism and audacity the dignity of rules. The American habit of analogy helps to keep this mental balance. Consider weather forecasts. A rainstorm that ruins a parade is not a feud between clouds and brass bands. It is timing. We accept that and still pack umbrellas when the chance is high. Consider traffic lights. Sometimes you catch 5 greens in a row. the sequence feels like a reward for skill. It is a small miracle of synchronization that we only notice when it favors us. Consider national park geology. You can stand at the Grand Canyon and point from layer to layer, naming ages that dwarf nations. When a visitor at that scale crosses a date on our tidy wall calendar, the crossing feels staged. It is simply a brief overlap of two clocks that rarely tick in the same room. Another helpful frame is to ask what repeats. One path that mimics a planned tour could be chance plus our selection bias. Many paths over decades that mimic planned tours more often than models allow would be heavier. One perihelion that hides behind solar glare is frustration. Several that do so in ways that keep favoring the same secondary vantage points are a pattern that demands attention. We do not need to know the endpoint today to start keeping score. We need records that future minds can read without guessing at our methods. That means timestamps with clear uncertainties, pipeline code shipped with the data, and enough context to align the behavior of a tail with the behavior of the solar wind that washed over it. All of this lives within a social clock that ticks at different speeds for different players. News cycles want hours, telescope committees work in months, rocket schedules run in years, careers and public patience run somewhere in between. A coincidence invites hot takes on the shortest clock. The tests that can confirm or cool the mood live on longer ones. Keeping trust between those clocks is as important as keeping a magnetometer honest. Daily notes can say what tonight is for and what tomorrow will not settle. Weekly notes can teach one piece of physics that the audience will need next week. Longer notes can admit what we still do not know and what would convince us. None of this sells drama. It buys a steadier appetite for the kind of patience that real answers require. There is a final, gentler point about deep time that Americans know from family stories and national memory. Perspective grows when you add generations. When a grandparent describes a century as a handful of seasons, teenagers see their own years differently. The sky offers the same medicine in stronger doses. If we can sit with spans that run beyond our span and still find meaning in smaller arcs, our urge to insist on cosmic intent in every overlap begins to quiet. We can enjoy the poetry of a traveler cresting the sun when our view is worst without turning poetry into policy. We can let wonder stand on its own feet. None of this empties the room of purpose. It sets a higher bar and a clearer aisle to walk down if purpose ever shows itself. If a pattern is real, it will survive the sober tests we design. If a plan is real, it will make promises that more data either keep or break. If neither survives, we will still have used the moment to teach a nation how to read the sky with fewer shortcuts and more grace, which leads naturally to the crowded ground where sky stories meet everyday life. When a mystery hums for weeks, feeds scroll, and school kids ask questions at dinner, people want to know what is safe to assume, what is worth ignoring, and how to follow along without being bounced between thrill and letdown. They want to know how rumors grow, how to spot a mislabeled image, how to understand a distance when the word close has already planted a picture in their heads. They want to know when experts are guessing and how to tell a guess from a measurement when the language is polite. That is the terrain of risk, safety, and straight talk. And if we hope to leave this season wiser than we entered, it is where our attention must go next. When a sky story grows loud, risk stops being an equation and becomes a feeling. People in American cities and small towns hear words like close and aligned, and they picture incoming danger. They look up during a school pickup, they scroll at midnight, and they want simple answers. Are we safe? What is real? What is noise? What can we do that is useful? A healthy script meets those questions without drama and without shrinking from uncertainty. It walks two tracks at once. One track deals with the world of machines, fields, and particles. The other deals with the world of rumor, trust, and attention. If we tend both tracks with the same care, the next visitor will leave us steadier rather than jumpier. Begin with the plainest safety truth. A fast interstellar body passing through the inner solar system is not automatically an impact threat. Its path is measured, updated, and watched by many teams that publish numbers with dates attached. If a real hazard to Earth existed within a practical window, the notice would come with calendar times, distances in miles, and a plan for follow-up measurements. In most seasons, the geometry that makes an object hard to see near the sun is the same geometry that keeps it far from Earth. Hard to see does not mean headed our way. It means glare is in the way. There are real risks that live far from ground level. Spacecraft that wander into the densest parts of a dusty envelope can be sandblasted at high speed. Engineers plan for this with shields that break incoming grains before they reach the main wall. Operators plan for it by steering around the brightest fog when they can. Satellite operators near Earth watch for solar storms that can arrive during the same week and complicate the story. A power fluctuation in the Midwest or a brief radio dropout on the coasts may be driven by the sun, not by a visitor. And that distinction matters for how utilities and agencies respond. The cure for confusion is a clean timeline that puts each event on its own clock and shows how one followed from another. The sharper risks are social. A rumor that promises a reveal, a secret signal, or a silenced expert spreads faster than a correction because the rumor offers the reader a role. The reader becomes an insider. Good public communication offers a better role. It invites people to follow a calendar, to watch specific measurements arrive on schedule, and to grade claims against outcomes. When the audience can check boxes with their own eyes, patience becomes less like waiting in a line and more like playing a season. Words are safety tools. Close has one meaning in an observatory and another at a kitchen table. Close can be tens of millions of miles away, a vast gulf that instruments love and humans need not fear. Aligned can mean nothing more than sharing a small angle in the sky, not pointing or aiming. Unusual can mean rare in the training diet of a computer model, not forbidden by nature. A script for a broad American audience puts numbers beside those words. It writes miles and dates. It avoids promising a thunderclap on a specific Thursday. It repeats the next landmark so that newcomers can step in without feeling lost. Uncertainty is not a flaw to hide. It is a dial that tells you how much to trust a claim and when to check back. People already live with such dials in weather reports, polls, and medicine. They can live with them in space stories if we keep the dial in the same place week after week. The routine is simple. Say what is firm this week. Say what depends on next week's angle or instrument. Say what cannot be known. Without a mission, we have not yet flown. Then keep the appointments you set. The credibility you build this way will carry you through the next season when temptation to overpromise returns. Media habits can either steady or shake the room. A layered cadence works best. Give a daily paragraph that says tonight's goal in one sentence. Add a short explainer that teaches a single idea that will matter tomorrow, like why a tail can snap and grow again when a solar shock arrives. Post a less frequent, longer note that answers recurring questions in simple English. Keep 3 anchors pinned to the top of every update. A master timeline with absolute times. A glossary whose definitions do not drift. A single chart that shows the core orbital quantities as ranges rather than razor lines. These anchors look boring. They prevent a dozen small panics. Creators with big audiences can be powerful allies if they adopt a few rules. Label simulations as simulations and artist impressions as art. Never announce a day of revelation. Announce windows with start and end times and explain why they might slip. Do not post a single number when a range is honest. If a distance could be between 2 values, say so. The audience does not flee when treated as adults. They stay because the respect feels rare. Practical viewing safety belongs in every American script when a bright object moves near the sun. Never look at the sun without proper solar filters designed for direct viewing. Do not jury-rig filters for binoculars or cameras. If a safe evening opportunity appears to see a tail far from the sun, local astronomy clubs will say so and will share best practices for dark sky viewing. If a product promises secrets through a phone camera and no eye protection, treat it like a miracle diet. There is a subtler kind of safety that lives in budgets and attention. Hype can steer donations and energy towards souvenirs of a feeling rather than toward instruments, archives, and training. That current can be turned gently. Agencies and observatories can point curious people towards citizen science projects that ask for specific images taken in specific ways. They can invite support for open data vaults where raw frames are stored for future students. They can host nights where visitors see raw numbers on a screen turn into a graph with their own eyes. Receipt for belonging beats receipt for merchandise, and it leaves the ecosystem stronger. Inside the research community, there is a kind of moral safety to defend. Overclaiming burns trust. So does hiding doubt. The answer is not to turn every update into a seminar. It is to choose sentences that will not embarrass you later and to say aloud what would change your mind. If you are going to call a path efficient, say what would count as inefficient next week. If a machine learning flag drove attention, say how the label would change if the training diet changed. When a result contradicts your earlier favored story, put the contradiction in the headline of your own note. That is not self-punishment. It is the path to durable authority. Journalists do their best work when scientists meet them halfway. Offer numbers with ranges and clear units. Explain one or two terms that will unlock the future stories, like how a viewing angle changes the look of a surface, or how sunlight and heat can nudge a path in subtle ways. Do not hide behind jargon like gravitational acceleration. Say that a warm side pushes a little more than a cool side, and that over weeks those pushes add up. Clear sentences fight panic more effectively than scolding does. Schools are part of safety too. A classroom that graphs a light curve and reads a legend will not be fooled by a mislabeled animation next year. A teacher who turns a nightly update into a lab plot. Fit. Compare gives students a feeling for noisy data that no lecture can match. Those students will ask for timestamps, for units, for raw frames. They will be first in line to help when the next campaign asks for 1,000 small telescopes to keep a cadence through bad weather. Policy and funding can either reward steadiness or amplify drama. Standing budgets for rapid targets, shared ground stations, and open pipelines look unexciting until the night you need them. After that, they look like wisdom. Legislators do not need to master plasma physics to help. They need to hear one pledge, repeated by scientists with a straight face. A null result announced on time is a win if it closes a door cleanly. When agencies reward that pledge, teams stop leaning on cliffhangers to justify their work. The public learns to admire execution rather than spectacle. Errors will happen. A ghost in a camera will look like a jet. A local radio interference source will masquerade as a line from space. A plot will go out with a mislabeled axis. The reputational damage from the error is not set by the error itself. It is set by how quickly the correction travels and how plainly it speaks. Put the fix in the same feeds and with the same energy as the original. People do not punish honesty. They punish the sense that someone hoped to edit the record quietly. Artificial intelligence sits in the middle of many new scripts and deserves an honest seat. If a model helps sort tracks by rarity, say what it learned on. If it flags a case, say whether the flag is rare because the path is truly unusual or because the training set was light on interstellar examples. If you change the cost of missing a real oddity versus the cost of crying wolf, say that too. These details give the audience a way to weigh a label and give other teams a way to reproduce or challenge the claim. For everyday followers in the United States, a small personal checklist goes a long way. Read distances with miles attached. Read dates with time zones. Prefer updates that show their clocks and their methods. Treat any claim that does not link to a process as entertainment. Enjoy it if you like, but do not make plans around it. When you see a dramatic image, ask whether it is a simulation or a photograph, and whether the caption says how it was made. When a post hints at a reveal on a specific day, expect a letdown. When a post invites you to watch a test that will arrive within a stated window and then grades itself in public, expect to learn something even if the result is quiet. None of this drains the wonder. It builds a way to carry wonder forward without being whiplashed by every rumor. A calm, repeatable rhythm of measurement and reporting makes the next extraordinary season easier to live through. It also sets the stage for the question that has been humming under every paragraph since we began. If the story of 3IT Atlas turns out to be a coincidence dressed in geometry, we will have learned a more careful way to read the sky. If the story turns out to include purpose, we will be ready to recognize it because we took care with our clocks, our words, and our tests. Either way, the last move is the same. We close the loop with the question we started with, and a promise to keep our curiosity brave and our claims modest, which is where the final part now takes us. We began with a simple unease and a narrow window. 3I Atlas would skim the sun just when Earth's view turns harsh with glare, and our memories of Oumuamua and Borisov sat on either shoulder like mismatched advisors. A learning system labelled the route unusual, and the oldest question returned in a new coat: coincidence or design? We answered it the only way that lasts. We drew a clean timeline. We let geometry and plasma have their say. We read heat and dust as patiently as we read headlines. We imagined a hidden craft and turned the fantasy into tests that instruments could keep or break. We built a culture that treats a timely null as a kind of victory. None of these forces a verdict today. It raises the threshold for what would count as proof and hands that threshold to anyone willing to watch along. If a plan is there, it will survive better phase angles, steadier clocks, and the next round of quiet measurements. If chance is the author, it will look more like chance as the catalogue grows and our training diets improve. So we keep our promises. We will publish when the object clears the sun. We will compare before and after with the same care we used to imagine intentions. We will let wonder breathe and let evidence lead. If you want the next chapter the moment it writes itself, keep your calendar marked. The sky moves on its own time. We can meet it with ours.